From a distance, the universe looks calm. Stars burn steadily. Galaxies drift slowly. The night sky feels stable and orderly. But that calm is an illusion created by scale. Scattered across the cosmos are objects and events so extreme that on paper they shouldn't exist at all. Not because they break the laws of physics, but because they push those laws to their absolute limits. Tonight, we're exploring the most extreme objects known to exist, stars that crush matter beyond atomic structure, magnetic fields that distort space itself, explosions that briefly outshine entire galaxies. These are not hypothetical dangers. They are real, observed outcomes of physics operating without compromise. And despite how violent they sound, almost none of them threaten Earth. They exist safely across vast distances, isolated by scale and geometry. Their importance isn't what they could do to us, but what they reveal about how far reality can be pushed before it behaves in ways that feel almost alien. Before we go any further, if you enjoy exploring how the universe works beneath the surface, a like or subscribe genuinely helps the channel grow. With that, we begin not with distant catastrophes, but with the star that defines the limits of what can exist at all. The Sun appears calm because our perspective is forgiving. From 93 million miles away, it looks like a steady disk of light, rising and setting with reassuring regularity. But beneath that stability is a constantly shifting surface of plasma and magnetic energy, driven by nuclear reactions that convert millions of tons of matter into energy every second. The Sun is not burning in the conventional sense. It is fusing hydrogen into helium under pressures and temperatures that have no parallel on Earth, releasing energy that floods the solar system and makes life here possible. That same energy also powers the Sun's magnetic field, which twists and tangles as the star rotates and convects internally. When those magnetic fields become unstable, they snap and reconnect, releasing enormous bursts of radiation known as solar flares, often accompanied by coronal mass ejections that launch billions of tons of charged particles into space at incredible speeds. These events can carry enough energy to disrupt satellites, interfere with radio communication, and induce electrical currents in power grids across entire continents. We know this not from speculation, but from experience. Earth has already been struck by severe solar storms, most notably in the 19th century, when electrical infrastructure was primitive enough to visibly fail under the Sun's influence. In today's technologically dependent world, a similar storm would cause disruption, economic damage, and temporary instability. And yet, even at its most extreme, the Sun remains fundamentally constrained. Earth's magnetic field deflects most incoming charged particles, while our atmosphere absorbs high-energy radiation before it can reach the surface. The same storms capable of damaging electronics also produce auroras, harmlessly painting the sky with visible evidence of invisible forces. Life itself is not threatened. The Sun is powerful, but it operates within boundaries that make long-term stability possible. This balance is not accidental. It is the reason Earth exists at all. The Sun represents the upper limit of what a life-supporting star can safely be, violent enough to be dynamic, stable enough to persist for billions of years. It is our first lesson in cosmic extremity. Immense power does not automatically translate to catastrophe, but the universe is not limited to stars like ours. When stars far more massive than the Sun reach the end of their lives, the balance between outward pressure and inward gravity collapses completely. The core implodes under its own weight, compressing matter so violently that electrons and protons are forced together, forming neutrons. What remains is a neutron star, an object with more mass than the Sun contained within a sphere no larger than a city. The density is so extreme that matter no longer behaves in familiar ways. Atomic structures are crushed beyond recognition, leaving behind a tightly packed lattice of neutrons held together by gravity alone. On these surfaces, gravity is strong enough to distort space itself, and time slows measurably compared to distant observers. A single teaspoon of this material would outweigh entire mountain ranges. Some neutron stars push even further into unfamiliar territory. Known as magnetars, they possess magnetic fields so powerful that they exceed anything else known in the universe. These fields are not merely strong, they fundamentally alter the behavior of matter. At close range, they would disrupt chemical bonds, deform atoms, and interfere with biological processes before any physical contact occurred. Despite this, magnetars are not cosmic executioners. They are rare, short-lived, and distant. Their most violent outbursts, detectable across the galaxy, register on Earth as faint flashes of high-energy radiation that pose no threat to life. Their danger exists almost entirely in theory, because the universe keeps them safely isolated by scale and distance. What makes magnetars important is not what they could do to us, but what they demonstrate about reality. They reveal how matter behaves when forced into conditions that no laboratory could ever reproduce. They show that physics does not stop at familiar states, but continues into regimes where intuition fails and equations take over. They are not warnings, they are confirmations. Few objects have been so thoroughly misunderstood as black holes. Popular imagination often treats them as active agents of destruction, roaming the universe and consuming everything in their path. In reality, black holes are remarkably passive. They do not hunt. They do not pull harder than any other object of equal mass. From a distance, their gravitational influence is indistinguishable from that of a star. Most black holes form when massive stars collapse, inheriting their mass and little else. If the Sun were somehow replaced by a black hole of equal mass, Earth's orbit would remain unchanged. Nothing dramatic would happen. The danger associated with black holes exists only at extremely close distances, where tidal forces become overwhelming. Even so-called rogue black holes, drifting through the galaxy after being ejected from their birth environments, are not threats. Space is incomprehensibly vast, and the probability of one passing near a planetary system is vanishingly small. Even in the unlikely event of a close encounter, gravitational effects would be gradual and detectable long before any catastrophic outcome. Black holes are extreme not because they are destructive, but because they represent the ultimate consequence of gravity. They mark the boundary where known physics begins to fail, where space and time behave in ways that challenge our understanding, and where information itself becomes an open question. Their significance is intellectual, not existential. They force us to confront the limits of our theories and the structure of reality itself. Black holes are not lurking dangers. They are quiet endpoints. At the centers of nearly all large galaxies, including our own, lie objects so massive that they reshape their surroundings on scales measured in thousands of light years. These are supermassive black holes containing millions to billions of times the mass of the Sun, embedded deep within the gravitational architecture of their host galaxies. Unlike the dramatic portrayals often associated with black holes, these objects spend most of their existence in a state of near total silence, exerting influence not through constant destruction, but through long-term gravitational order. In their active phases, when gas and dust fall inward, supermassive black holes become the engines that power some of the brightest phenomena in the universe. Material spiraling toward the event horizon forms an accretion disk that heats to extreme temperatures, releasing torrents of radiation and launching jets of particles that can extend far beyond the galaxy itself. These active galactic nuclei and quasars can outshine entire galaxies, briefly becoming the most luminous objects in existence. And yet even here, danger is not the defining feature. These outbursts are not random acts of violence. They are regulated processes that play a role in galactic evolution, shaping star formation by heating and redistributing gas. Over cosmic timescales, supermassive black holes act less like destroyers and more like regulators, influencing how galaxies grow, mature, and eventually settle into stability. From Earth, even the nearest of these giants pose no threat. The black hole at the center of the Milky Way is quiet, consuming little material and exerting no disruptive influence on the solar system. Its gravity, immense though it is, fades predictably with distance, leaving our region of the galaxy dynamically calm. What makes supermassive black holes unsettling is not what they do to us, but what they reveal about scale. They demonstrate that gravity can organize matter across distances so vast that individual stars become irrelevant, and that the most powerful engines in the universe can operate invisibly for billions of years, shaping cosmic history without ever announcing themselves. If there is any phenomenon that seems at first glance genuinely apocalyptic, it is the gamma-ray burst. These events release more energy in seconds than the sun will emit over its entire lifetime, producing narrow beams of radiation intense enough to sterilize planets at close range. For a brief moment, a gamma-ray burst can rival the combined output of all the stars in a galaxy. They occur when massive stars collapse into black holes, or when compact objects like neutron stars merge, focusing enormous amounts of energy into tightly collimated jets that pierce through surrounding material at near light speed. The key word here is focused. Gamma-ray bursts do not explode outward in all directions. They are cosmic flashlights, emitting energy along extremely narrow paths. This is why, despite their power, they are not existential threats to Earth. The probability of a gamma-ray burst occurring close enough, oriented precisely toward our planet, within the window of complex life's existence, is extraordinarily small. Most gamma-ray bursts occur billions of light-years away, their radiation diluted long before it reaches us. Even those within our galaxy are exceedingly rare, and orientation matters more than distance. We detect gamma-ray bursts not because they endanger us, but because they illuminate the most extreme conditions under which matter and energy interact. They provide insight into stellar death, relativistic physics, and the behavior of space-time under enormous stress. Their fleeting nature makes them difficult to study, but also ensures they leave little lasting imprint on their surroundings. Gamma-ray bursts feel unsettling because they compress cosmic power into humanly comprehensible timescales. They remind us that the universe can release extraordinary energy without warning, but they also demonstrate how vast space truly is, acting as a buffer that renders even the brightest cosmic catastrophes distant and harmless. Among the most extreme stellar deaths ever theorized are pair instability supernovae, events so violent that the star responsible does not leave behind a remnant of any kind. No neutron star, no black hole. The star simply annihilates itself, dispersing all of its material into space in a single catastrophic detonation. This process occurs only in stars of extraordinary mass, far larger than those commonly found in the modern universe. In these stars, the core becomes so hot that high-energy photons spontaneously convert into pairs of electrons and positrons, reducing the radiation pressure that normally supports the star against gravity. The balance collapses, the core contracts, and nuclear reactions run out of control, releasing enough energy to tear the star apart entirely. The result is an explosion of almost unimaginable scale, enriching surrounding space with heavy elements while leaving no central object behind. These events are thought to have been far more common in the early universe, when stars formed with much greater masses due to the lack of heavy elements that limit star size today. Despite their power, pair instability supernovae are not hazards. They occur in distant galaxies and ancient epochs, separated from Earth by both space and time. Their importance lies in their role as cosmic forges, seeding the universe with the elements necessary for planets, chemistry, and eventually life. There is something quietly profound about these stars. They do not collapse into denser forms. They do not persist as gravitational scars. They end their existence by giving everything back to the universe at once, contributing to future generations of stars rather than anchoring themselves as remnants of destruction. They are reminders that even the most extreme cosmic events can be creative rather than ruinous, destructive only in the narrow sense and essential in the broader story of how complexity emerges. When people imagine danger in the universe, they usually picture violence, explosions, collisions, radiation. But one of the most extreme features of cosmic structure is not defined by excess, but by absence. On the largest scales, The universe is not evenly filled with galaxies. Matter arranges itself into vast filaments and walls, leaving behind enormous regions where almost nothing exists at all. These regions, known as cosmic voids, can span hundreds of millions of light years. Within them, galaxies are rare, isolated and widely separated, drifting through expanses of space so empty that even intergalactic gas becomes scarce. From within such a void, the universe would appear stark and quiet, with few nearby galaxies to illuminate the darkness. This emptiness is not accidental. It is a natural consequence of gravity, amplifying tiny density differences present in the early universe. Regions that began slightly denser accumulated matter and grew into filaments and clusters, while regions that began slightly emptier expanded faster, becoming increasingly devoid of structure. Over billions of years, the contrast sharpened, producing a universe defined as much by what is missing as by what is present. Despite their immense scale, cosmic voids are not hostile places. There is no force pushing outward, no energy waiting to be released. They are simply regions where gravity had little to work with. Their significance lies in how they reveal the large-scale geometry of the universe and the influence of dark matter and dark energy on cosmic evolution. Voids remind us that extremity does not always mean intensity. Sometimes the most extreme condition is near total emptiness, stretched across distances so large that even galaxies become statistical outliers. And yet, even this vast nothingness poses no threat. It exists quietly, shaping the universe through absence rather than action. Some of the most visually dramatic structures in the universe are not explosions, but beams, relativistic jets launched from the vicinity of supermassive black holes. When material falls into these black holes in a steady stream, magnetic fields can channel part of that infalling matter into narrow jets that erupt from the galaxy's core at speeds approaching that of light. These jets can extend for hundreds of thousands, sometimes millions of light years, punching through intergalactic space and depositing energy far beyond their point of origin. In radio wavelengths, they reveal enormous lobes of energized plasma, tracing the long-term influence of a black hole's activity across cosmic distances. At first glance, such jets appear violently directional, as though galaxies themselves are firing weapons into the universe, but this impression dissolves under closer examination. The jets are highly collimated and narrowly confined. Outside their immediate path, their influence drops rapidly. Entire galaxies can coexist beside these structures without disruption, separated by distances that render the jets effectively harmless. For Earth, the risk is negligible. Our galaxy does not host an active jet, and even if it did, the odds of precise alignment with the solar system would be vanishingly small. Like gamma-ray bursts, jets are dangerous only in theory, requiring a precise geometry that the universe rarely provides. Their importance lies elsewhere. Relativistic jets show how black holes can transfer energy from tiny regions of space-time to scales that rival entire galaxies. They reveal how magnetic fields, gravity, and relativistic motion combine to produce ordered structures out of chaos. And they demonstrate that even the most powerful engines in the universe operate within strict geometric limits. The jets are not expressions of aggression. They are the universe finding efficient pathways to redistribute energy, carving patterns into space that persist long after the central engine has quieted. Beyond individual objects and events lies a deeper category of extremity, the large-scale behavior of the universe itself. Expansion is not an explosion into empty space, but the stretching of space everywhere at once. Galaxies are not racing outward through a static void. The distances between them are increasing because the fabric of space-time is expanding. This expansion has shaped everything we see. In the early universe, matter was dense, hot, and nearly uniform. Over time, expansion cooled the cosmos, allowing particles to form atoms, atoms to form stars, and stars to assemble into galaxies. Without expansion, gravity would have collapsed everything back into a dense state. Without gravity, expansion would have left the universe empty and structureless. The balance between these forces is delicate, yet persistent. Even now, billions of years after the first stars ignited, the universe continues to evolve in a slow, measured way. Expansion accelerates under the influence of dark energy, gradually isolating galaxies from one another, stretching space until distant regions slip beyond observable reach. This process can feel unsettling when framed in human terms, as though the universe is pulling itself apart. But nothing catastrophic is occurring locally. At the scale of galaxies, stars, and planets, gravity easily overwhelms expansion. The solar system remains bound. The Milky Way remains intact. Life continues unaffected. What expansion reveals is not danger, but context. It shows that the universe operates on timescales so vast that even its most dramatic changes unfold with glacial slowness from our perspective. The cosmos is not resetting itself through sudden catastrophe, but through gradual transformation measured in billions of years. The extremity lies not in violence, but in patience. The universe changes everything eventually, not through sudden destruction, but through relentless, quiet evolution. After moving through the universe's most extreme phenomena, a pattern begins to emerge that is easy to overlook when focusing on power alone. Nearly all cosmic danger diminishes rapidly with distance. Energy spreads out, radiation weakens, gravitational influence fades. Space itself acts as a vast buffer, separating violent processes from regions where stability can persist for billions of years. This is not a coincidence. It is a direct consequence of how the universe is structured. Stars are separated by light years, galaxies by millions of light years. Even within galaxies, planetary systems occupy tiny, isolated pockets compared to the vast emptiness between them. Most of space is not crowded with hazards. It is overwhelmingly empty. This emptiness matters. It ensures that even the most energetic events, supernovae, gamma-ray bursts, relativistic jets, affect only small volumes relative to the size of the universe. Their intensity drops sharply beyond their immediate surroundings. To be harmed by them requires not just proximity, but extraordinarily precise alignment in both space and time. Earth benefits from this separation in countless ways. We orbit a star located far from the crowded galactic center, in a region with relatively low stellar density. Nearby massive stars are rare. Potentially disruptive events are infrequent. The distances involved are so large that even when catastrophic events occur elsewhere in the galaxy, their effects reach us as faint signals rather than destructive forces. The universe does not protect us intentionally. It simply follows geometric rules that favor separation over congestion. Distance is not just an inconvenience for exploration. It is a stabilizing feature that allows complexity to persist. What appears dangerous in theory becomes harmless in practice, not because the universe is gentle, but because it is vast beyond everyday comprehension. When all of these extremes are considered together, it becomes clear that our local environment is not typical of the universe's most energetic regions. The solar system exists in a comparatively quiet neighborhood, far from the violent cores of galaxies, far from dense star clusters, and far from the kinds of massive stars that live fast and die explosively. This calm is not fragile. It has persisted for billions of years. The sun's output varies slowly. Nearby stars move predictably. Galactic tides are weak. The night sky changes so gradually that human civilizations can rise and fall without noticing any difference at all. From a cosmic perspective, this stability is remarkable. Many regions of the universe do not enjoy such long-term consistency. Starburst galaxies experience frequent supernovae. Dense clusters subject planets to gravitational disruption. Active galactic nuclei flood surrounding space with radiation. Compared to these environments, our region is subdued. But calm does not mean exceptional in a mystical sense. It simply reflects probability. In a universe so large, regions of relative tranquility are inevitable. We exist in one not because it was designed for us, but because only in such regions can observers exist long enough to wonder about the universe at all. This is not a comforting thought in the emotional sense, but it is a clarifying one. The universe does not need to be safe everywhere. It only needs to be safe somewhere, and somewhere, for now, happens to be here. The most unsettling aspect of the universe is not that it contains objects capable of unimaginable destruction. It is that those objects are natural, inevitable outcomes of simple physical laws applied at extreme scales. Gravity compresses matter. Nuclear reactions release energy. Magnetic fields organize motion. When conditions allow these processes to run to their limits, the results appear alien only because they lie so far outside everyday experience. Yet none of this implies hostility. The universe is not chaotic in the sense of being unpredictable. Its most extreme phenomena follow the same rules as its calmest ones. The difference lies in scale, not intent. Understanding these extremes does not diminish our place in the cosmos. It sharpens it. It shows that life does not exist in defiance of the universe, but within a narrow, stable corridor carved out by distance, time, and probability. The same physics that produces magnetas and black holes also produces long-lived stars, quiet orbits, and environments where complexity can slowly emerge. When we look out into the universe and catalogue its most powerful objects, what we are really doing is mapping the boundaries of possibility. We are learning how far reality can be pushed before it behaves in ways that feel unfamiliar. And in doing so, we gain a clearer picture of where we are within that spectrum. The universe is vast, strange, and capable of extremes beyond imagination, but it is also patient, spacious, and remarkably consistent where it matters. Earth is not standing on the edge of disaster. It is floating within a long-lived pocket of stability, surrounded by phenomena that are awe-inspiring precisely because they are distant. In the end, the universe's most extreme objects are not reminders of our vulnerability. They are reminders of scale, of how much room reality has to explore its own laws without ever needing to touch us at all.